So, homework number 9 on chapters 10 and 11 is due on the 4th. We should be done with chapters 10 and 11 before the Thanksgiving break. So you'll have that entire time plus a little longer. The exam on chapter 10 and 11 and maybe a little bit of 13, because it looks like the next thing we're going to do is chapter 13, will be on the 11th. That's the last exam. We do have a lab this week on Wednesday. So we're running ahead of previous years, so we're probably also going to go cover chapter 13, but there won't be a homework assignment on it. So, we're going to start by talking about rotational. We're going to start with chapter 10. We're basically moving on from linear motion to rotational motion. We'll start with rotational kinematics and energy, and then we're going to talk about rotational momentum and things. So we'll start with rotational kinematics. Rotational kinematics are much like one-dimensional linear kinematics, except instead of motion in a straight line, we're dealing with rotation. So we'll talk about angular position, velocity, and acceleration, how angular position, velocity, and acceleration are related. The equations for this will be very familiar from back in chapter 2 when we were covering one-dimensional kinematics, because it's the same sort of relationship. Velocity is the derivative of position. Acceleration is the derivative of velocity. So we'll cover the rotational kinematics. We'll talk about the connections between linear and rotational quantities. So how to compare things like angular velocity to the actual speed of something moving around in a circle. Then we'll talk about rolling motion. Then we'll talk about rotational kinetic energy and the moment of inertia. And then lastly, we'll talk about conservation of energy and how conservation of energy gets a little more complicated once rotation comes in. Because basically, in addition to linear kinetic energy and potential energy, there's another form of kinetic energy that energy can go into, rotational kinetic energy. So you just have it basically adds a second kinetic energy to it. So let's start with angular position. How do we define angular position? Angular position is an angle measured from a reference line. Throughout this chapter and the next one, angles are all going to be measured in radians. That's because they make the math work. So the SI unit for angle is radians. And because of the way radians are defined as the arc length traveled divided by the radius. That's meters divided by meters. Radians are technically unitless. So radians technically are unitless. Oh, and I should have mentioned your grades for your exams are up and available. I'm not handing them back yet because there's still someone that needs to make up the exam. You all did, I think, better than last time, and last time you all did excellently. So not much you have to worry about. So radians are dimensionless because they're technically length over length. So the convention is that counterclockwise rotation is positive and clockwise rotation is negative. And that's just a convention. It's utterly arbitrary, but it's how all the math works. So, and if you go into 3 dimensions, the direction of rotation, you take your fingers and you curl them in the direction of rotation around the axis of rotation. The direction of rotation is the direction your thumb points. So counterclockwise rotation is out of the board. That's positive. Into the board. Clockwise rotation, that's negative. That's the right hand rule. And you have to use the right hand, because your left hand will give you the wrong answer. So, by convention, counterclockwise rotation from a reference line is positive, clockwise is negative. It's just how we set up our map. You could set up a system where those were reversed. But that's just the convention. Same way we measure angles. We measure from the x-axis counterclockwise. Yeah, like the unit circle. And yeah, negative you go clockwise. Positive you go counterclockwise. So 1 revolution is 2 pi. 1 revolution is 2 pi radians, or 360 degrees. That's sort of your general conversions. Because sometimes things are in like revolutions per minute, RPM, and you want to turn it into radians per second. The arc length is measured in meters. That's the distance you traveled around the circle. And your arc length, S, is equal to the radius times theta. Where theta is, the angle you travel. Angular velocity, omega. Actually, I'm going to move this over. Omega is d theta dt. Much like velocity is dx dt. Omega is angular velocity. The unit is radians per second, or technically inverse seconds. And if you were, yeah, 1 over seconds. So seconds to the minus 1. Oh. 1 over seconds. And the relationship, average omega is change in angle over change in time. Just like average velocity was. And the definition is the limit. Omega is d theta. This should be more clear. And this is an omega, the Greek letter omega, not a W. Isn't actually a lowercase w to worry about, but so again, positive omega, counterclockwise rotation, negative omega, clockwise rotation. So here, if you have a wind turbine for generating electricity that rotates clockwise at a rate of 17 RPM, 17 revolutions per minute, what is its angular velocity in radians per second? So this you need to convert from revolutions to radians, from minutes to seconds, and note that it is in the clockwise direction. Give you a little bit of time. Yes. So basically you have 17 revolutions per minute, and you'll need to convert revolutions to radians. So that's 2 pi radians over 1 revolution. And you'll need to convert seconds to minutes. So that's 1 minute over 60 seconds. And just multiplying through. So omega is theta over t, 17 revolutions over 1 minute. That's the way you can think of it. Or you can think about it as 17 revolutions per minute. So 17, each revolution is 2 pi radian, each minute is 60 seconds. So 17 times 2 pi divided by 60. So it's 106.8 radians over 60 seconds, which is 1.78 radians per second. So the general way you convert from RPM, revolutions per minute, to radians per second is you multiply by 2 pi divided by 60. 60 seconds in a minute. So there's 2 pi radians per revolution and 60 seconds in a minute. I get a little weird in this write-up.
Yeah.
But a revolution is 2 pi radians. That's what I substitute. And here we have a CD that rotates through an angle of 106 degrees in 0.860 seconds. So we want to find the angular speed of the CD in radians per second. And so again, 2 pi radians is 360 degrees. So you'll need to do a conversion. So the conversion is something like 106 degrees times 2 pi radians over 360. And that gives you your theta. Thank you again, myself. That's the angle, yes, 1.85 radians divided by the time. Omega is theta over t. Oh, just previous one. 106 degrees over 0.860 seconds. So 106 times 2 pi radians over 360 degrees. So 1.85 radians over 0.860 seconds, which comes out to an omega of 21.5 radians per second. Let me. I need to go through this quickly and start embedding. But we'll do that on the next problem. So, angular position, velocity, and acceleration. So we can define omega. Omega is angular velocity, but sometimes you're interested in like the period, how long it takes to make one rotation. The period ends up being 2 pi over omega. That's the angle it has to rotate through over the speed it's rotating at. The bigger omega, the shorter the period. Everybody's online. Pretty much everybody else is online. Nope. I think that's left over from a previous class. And then we can define angular acceleration, which is alpha, or as in the music we sometimes will get called fish. And alpha is just d omega dt. And the unit is radians per second squared. And because radians are once again unitless, that's 1/seconds squared, or seconds to the -2. And so angular acceleration, again, is the derivative of velocity. And if the angular acceleration is in the, again, here, so here are some examples. Here is a situation with an angular acceleration that is positive, and an angular velocity that is positive. It's rotating in the positive direction, counterclockwise, and it is speeding up. Here we have an example where the opposite is true. Both of them are negative. It's angular rotation, it's rotating in the clockwise direction. So the angular velocity is negative, and it's speeding up in the clockwise direction. So the angular acceleration is 0. Here we have, the weight is going up here. The rotation is counterclockwise, so it's negative, but the acceleration is positive. So the angular speed decreases when the acceleration and velocity have opposite signs. Here's the other example of opposite signs. Acceleration is negative, velocity is positive, angular speed is decreasing. So in all of these, the weight is pulling down, but in these two, it's also moving, unraveling. Well, these two are spinning opposite the weight, so the weight's slowing them down. So basically, this one is moving this way. The weight is going up, but slowing down that process. So here, given the formulas we have, let's find the period of a microwave tray that's rotating with an angular speed of 5 rotations per minute. Now, I'm going to go through and pause this stuff and then go through and make all the numbers bigger. Oh, this is, oops. Oh, my key has a mess up. Okay, sorry about that. I just need to enlarge all the numbers. So the period is going to be 2 pi over omega. So 2 pi radians over 5 RPM. So 2 pi radians over 5 rotations a minute times 2 pi radians per revolution divided by 60 seconds per minute, which is 2 pi radians over 0.1666666 radians per second, which comes out to a period of 12 seconds. The other way you can do this is the period is going to be 1 revolution over 5 revolutions per minute. So 0.2 minutes or 12 seconds. Sorry about the delay. I just needed to make all the numbers bigger so they were easier to see. So here we have a ceiling fan that was rotating with an angular velocity of 12.6 radians. Yeah, they're all on Blackboard. I just made the numbers bigger. They're on the next slide. I just had to go through and make all of these. Should be what's out there. I don't even think I have one that doesn't have it on there. Look at Blackboard really. Go to lectures. Cool. So here we have a ceiling fan that's rotating with an angular velocity that was rotating with an angular velocity of 12.6 radians per second. Begins to slow down when it's turned off. How much time does it take for the fan to come to rest if it has a constant angular acceleration of minus 1.68 radians per second squared? So these are going to be basic, angular acceleration is change in velocity, change in angular velocity over change in time. So you should be able to work this out. Basic equation is going to be acceleration is delta omega over, I guess you could write that with delta t, right? Change in omega over time. So alpha is delta omega over t. Omega is angular velocity.
Oh.
Alpha is angular acceleration.
Oh.
Velocity, acceleration. Omega is the equivalent of velocity. Yeah. This is going to end up just being that time is change in omega over acceleration. Did I? Oh no, those are apparently together for some reason. I screwed up the animations. That's all. So that's 0 minus 12.6 radians per second divided by minus 1.68 radians per second squared, which gives you 75 seconds. Because it's the change in velocity. It goes, this is final velocity minus initial velocity. So this is, omega final minus omega initial. So if you have constant angular acceleration, you get a kinematic equation that looks like this. Omega equals omega naught plus alpha. Oh, let me rewrite that. Alpha T. That should be familiar. This looks exactly like the kinematic equation for one-dimensional motion, except omega is replaced with, except V is replaced with omega, and A acceleration is replaced with alpha. Similarly, so this is an example of constant angular acceleration. You have a weight pulling down on the wheel. It has negative omega and negative alpha because it's moving clockwise and speeding up. And you can calculate how much it rotates with omega, how fast it will be rotating with omega with initial omega plus alpha t. Much like velocity equals v naught plus alpha t. Plus at. So there's an analogy between the linear and rotational kinematics. Basically, if you take the linear kinematic equations, all of these, and you replace x with theta, v with omega, and a with alpha, you'll get the rotational kinematic equations. So there, omega equals omega naught alpha t, theta equals theta naught plus omega naught t plus 1/2 alpha t squared, omega squared equals omega naught squared plus 2 alpha delta theta. There are equivalent versions of all of these equations. So if you remember them back from way back in chapter 2, you're just going to substitute theta for x, omega for v, and alpha for a. In general, these equations, we'll see there'll be something you substitute for the similar linear equations. So like when we get to energy, we're going to substitute something. Now, energy is 1/2 mv squared. We'll find energy for rotation is going to be 1/2 something times omega squared. And that something is going to be the replacement for mass. We'll get to it. So, if the angular velocity of the pulley below is minus 6.43 radians per second at a given time, and its constant angular acceleration is minus 4.91 radians per second squared. What's the angular velocity of the pulley after 1.25 seconds? So this is rotating in the negative direction. It's speeding up in the negative direction. It was starting at negative 6.43 radians per second. It's accelerating at negative 0.491 radians per second squared. And we want to know what the velocity of the pulley is 1.25 seconds later. Basic kinematic equation is omega equals omega naught plus alpha t. And we can really just plug the numbers in here. You know, negative 6.43 radians per second plus negative 4.91 radians per second squared times 1.25 seconds. And that gives us this, which is negative 7.04 radians per second. So here we have a certain game show that is not being named, though it should be obvious which game show it is. Contestants spin a wheel when it's their turn. One contestant gives the wheel an initial angular speed of 3.4 radians per second. It then rotates through 1.25 revolutions and comes to rest on the bankrupt space. Because apparently this contestant has excellent negative skills. So what is the angular acceleration of the wheel, assuming it to be constant? And how much time does it take for the wheel to come to rest? So you know the starting angular speed, you know the ending angular speed, you know the angle at which through it rotates, which is 2.5 pi. That's 1.25 revolution. And so what you want to do is find the acceleration, and then you want to find the time it takes to go through that process. This naturally breaks into two parts. The first part, to find the angular acceleration, well, you'll use this equation. So omega squared equals omega naught squared plus 2 alpha delta omega. So alpha is going to be omega squared minus omega naught squared over 2 delta theta. So 0 squared minus 3.4 radians per second squared divided by 2 times 1.25 times 2 pi radians, which is 2.5 pi radians times 2. So that was your negative 11.56 radians squared per second squared divided by 15.71 radians, which gives you negative 0.736 radians per second squared. That's the first part. The second part, once we know that, we can use omega equals omega naught plus alpha t to find the time. This rearranges to time equals omega minus omega naught over alpha. So 0 minus 3.4 radians per second divided by 0.736 radians per second squared, which is, minus 3.4 divided by minus 7.36 gives us 4.62 seconds. Now let's talk about the connections between linear and rotational quantities. Up here we noted the angular distance is the radius times theta, the angle would travel through. Well, a similar relationship exists. The tangential velocity is the radius times omega. Tangential velocity is the velocity around the circle. You could also have a radial velocity, which is moving in or out. But if you have a fixed circular path, you just have a tangential velocity. So the tangential velocity for this spinning object is how fast it's going around. And so tangential velocity is radius times omega, or omega is tangential velocity divided by radius. You'll notice this relationship where the linear term is just the radius times the angular term. Similarly, tangential acceleration ends up being alpha radius times alpha. I want to be consistent. Radius times alpha. Tangential speed is in meters per second. With tangential velocity, it's just radius times omega. So what's the angular speed a CD has to have to give a linear speed of 1.25 meters per second when the laser beam shines on the disk at a radius of 2.5 centimeters and a radius of 6 centimeters? This is something a CD drive actually does. CDs are designed so that the rate of rotation changes depending on how far from the center it's measuring. So it's got a constant linear speed, which allows it to pack more data in, basically. And interestingly, old laser discs, the earliest format of laser disc, didn't do that. It had constant angular speed, and that had some advantages. But there was also a format that used constant linear speed. And you both played on the same players, Like, you could have a laser disc. You could get more data on if you use constant linear speed than if you'd have more video on if you had constant linear speed. But you didn't have the tracking and stuff you had on the constant angular speed. So this fundamental equation is tangential velocity is radius times omega, which means omega is tangential velocity divided by radius.
No problem.
There's a huge stack of masking tape over there. That's better than this tape, I expect. This is like labeling tape, so.
Hey,
I mean, I might have some scotch. We do have some scotch as well. So at 2.5 centimeters, this omega is 1.25 meters per second divided by 0.025 meters. It's 50 radians per second. And then at 6 centimeters, 1.25 meters per second divided by 0.06 meters. That is 20.83 meters radians per second. So the CD drive is going to spin faster at 2.5 centimeters than at 6 centimeters. And that's something they actually do. They speed up as they get towards the center of the CD. Which is about 20.8 radians. Now, there are actually two forms of acceleration that an object has as it rotates. There is tangential acceleration, that's acceleration along the direction of rotation, but this is an object traveling in a circle. If it's traveling in a circle, that means its velocity is constantly changing. So any object that is moving in a circle has a constantly changing velocity and requires some form of acceleration to keep it moving in a circle. So that's centripetal acceleration. Centripetal acceleration is radius times omega squared, or tangential velocity squared over radius. This is the acceleration you feel if you go around a corner. This is the acceleration that's used, that's provided to keep you, that keeps something traveling in a circle. It can be provided by when I'm spinning this object around. The centripetal acceleration is being provided by the string, and at the top, it's also being helped by gravity. So if you're centripetal, if you're moving fast enough, if your centripetal acceleration is greater than the acceleration of gravity, then you can flip upside down without issue. That's how roller coasters work. There's also tangential acceleration. Tangential acceleration is just radius times alpha. So tangential acceleration is due to changing angular speed. This is when the rotation is speeding up or slowing down. Centripetal acceleration is due to changing direction of motion. So it is a function of the angular speed. You can have no angular acceleration, you will still have centripetal acceleration. Centripetal means center seeking. The direction of centripetal acceleration is towards the center of the circle. It's radial towards the center of the circle. So here's a merry-go-round that's speeding up. So this merry-go-round has both tangential and centripetal acceleration. You want to find the total acceleration. They're at right angles to each other. You can just add them together like any two things at right angles to each other. They're vectors at right angles. So here we have two children riding on a merry-go-round with child 1 at a greater distance from the axis of rotation than child 2. Is the angular speed of child 1 greater than, less than, or the same as the angular speed of child 2? And which of the following is the best explanation of your prediction? Now, this is angular speed. So is it 1? Child 1 is moving faster than child 2 and hence has greater angular speed. 2, child 2 is closer to the axis of rotation, which results in a greater angular speed. Or 3, both children complete a revolution in the same time, so their angular speeds are the same. Which of these is the correct description? Yep. The velocities are different, but the angular speeds are the same because they're on an object. They're rotating together. They're rotating at the same rate. But child 1 will be moving faster than child 2. So here's an example of centripetal acceleration being used for something. Oh, we are going fast.
So was it 1 or 2?
It's 3. This one.
Child 1 is faster than child 2.
Its linear speed is faster.
Right.
Its angular speed is the same.
Like they'll feel like the child 1 feels like they're more faster than child 2.
Child 1 is moving at, I don't know, this looks like child 1 is about twice as far as child 2. So if child 2 was moving at 1 meter per second, child 1 was moving at 2 meters per second. But they both maybe are moving. Child 2 is about 1 meter away. Child 1 is about 2 meters away. They're both moving at 1 radian per second. So the merry-go-round is rotating at the same speed, but the further out part is moving faster. Yeah, and you'll actually feel more centripetal acceleration. So notice how centripetal acceleration is radius times omega squared. So you feel a bigger centripetal acceleration further away from the center. But if you figure out the linear speed, it ends up being the linear speed divided by the radius, squared divided by the radius. So if you're driving in the car, you feel more centripetal acceleration when you go the same speed around a tight corner as opposed to same linear speed around a tight corner than a broad corner. So a centrifuge is something that uses rotation to generate an acceleration which separates things. The things with more mass and more inertia get moved to the bottom of the tubes. So in a microhemocrate centrifuge, small samples of blood are placed in a heparinized capillary tube. The heparin is an anticoagulant because you don't want it to turn into a solid lump. Doesn't separate as well. The tubes are rotated at 11,500 rotations per minute, with the bottoms of the tubes 9.07 centimeters from the axis of rotation. So what's the linear speed of the bottoms of the tube, and what's the centripetal acceleration of the bottoms of the tube? So you need to figure out linear speed. You're going to need to figure out you'll need to convert from rotations per minute to radians per second. And then you'll need to find the centripetal acceleration. Centripetal acceleration is radius times omega squared. And linear speed is radius times omega. So that's omega. So linear speed is radius times omega. First, let's find omega in radians per second. So omega is going to be 11,500 rotations per minute times 2 pi radians per revolution, divided by 60 seconds per minute. That's the conversion from RPM to radians per second. So our omega is 12,004.28 radians per second. So omega is, so the tangential velocity is the radius, 0.0907 meters, times omega, 1,204.28 radians per second. So the ends of those tubes are traveling at 109.228 meters per second, or rounded to three significant figures, 109 meters per second. Centrifuges go fast. uh, Then, if we want to figure out the centripetal acceleration, so oops, let me go back up to this. If we want to get the centripetal acceleration is radius times omega squared. So again, omega is 1,204.28 radians per second. So 0.907 meters times 1,204.28 radians per second quantity squared gives you a centripetal acceleration of 131,541 meters per second squared, which rounds to 132,000 meters per second squared, or something like 12,000 G is how that would be rated. Not 12,000, 1,200 G. I miscalculated. I misread my calculator. Oh wait, no, I was looking at the wrong number anyways. about 13,000 G. Because you're basically dividing by 10. Yeah. Well, that 13,400 G. So this is a nice centrifuge. And I mean, we could compare it to one of the ones we have in the lab over there. You know what? Because we're running ahead of schedule, I'm gonna go look. I'll be back in a second.
Oh. Monday, Tuesday, I'm bartender and then take on the beer.
Well, the fence pieces over there have some enormous range. It looks like they go up to something like 20-odd thousand G. It's variable. There's a button to set it, so I was just poking around. And so, those apparently are nice. Well, about twice as fast as this example. I mean, I can look at the numbers, but there wasn't a quick number I could read there. It also gives numbers in RPM. You can set it either way on the machine. So this is just a review of what we were talking about. This is that same problem. So let's quickly go over the idea of rolling motion. So when something rolls without slipping, there's a nice fixed relationship between the translational and rotational speed, because every rotation, it has to move one circumference horizontally. So the velocity ends up equaling the radius times omega. The velocity of your wheel that's rolling ends up equaling the tangential velocity of the outside of the wheel from the point of view of the wheel. Yeah, VT means tangential velocity. So that's, if the wheel was just on its own and spinning, it's how fast the edge of the wheel was going. It's how fast the edge of the wheel is going compared to the center of the wheel. That's a way to think about it. And that ends up, if you're rolling without slipping, that ends up being also the velocity, the linear velocity of the whole wheel. Yeah. Yeah, so basically, because the bottom of the wheel doesn't move relative to the ground. And so the bottom of the wheel is moving at the tangential velocity backwards relative to the center of the wheel. So the center of the wheel has to be moving forwards at the tangential velocity. But the bottom of the wheel isn't actually moving relative to the ground. And the top of the wheel ends up moving twice the tangential velocity relative to the ground. So basically, it's the addition of pure rotational motion with translational motion, such that the velocity at the bottom is 0, the velocity at the middle is R times omega, the velocity of the top is 2R times omega. So the rotational motion gives you a velocity of R omega forward and a velocity of R omega backwards. And then the translational motion gives you a velocity of R omega forwards everywhere. So they cancel out at the bottom, and you get increasing velocity as you go on. So if you have a car with tires with radius 31 centimeters, it drives on the highway at 31 meters per second. What is the angular speed of the tires? And what is the linear speed of the tops of the tires? So remember, we got velocity equals omega times radius. So basically, this is sort of the sketch of this. Velocity equals the tangential velocity, which equals radius times omega. Oh, I forgot to embiggen this. But this was on the next slide. This is the last thing I'm going to do for today anyways. So omega equals velocity over radius. So 31 meters per second divided by 0.31 meters. Omega is 100 radians per second. The top of the velocity of the top will end up being 2 times the velocity. So 2 times 31 meters per second is 62 meters per second. That's sort of all I wanted to cover for today. Yeah. See you on Wednesday. We'll have a lab on Wednesday. We'll go back over this again then. The next so the mastering on these chapters 10 and 11 is due December 5th. It's in a few weeks. After Thanksgiving break. Yeah, no, it's okay. We're done. So I'm gonna stop sharing. And you guys can head out. Gonna end the meeting soon. Oh, and Sam, can you please email me and let me know your plans regarding the makeup? That's all. I'm gonna end the meeting for all.